All right, this morning, I'm really excited to introduce our speaker today, Dr. John Drake. Dr. Drake is a distinguished research professor at the University of Georgia with affiliations in the Odom School of Ecology, the Biomedical and Health Sciences Institute, and the Faculty of Infectious Diseases. He is also the Associate Dean for Academic Affairs in the Odom School of Ecology, and the founding director of both their Population Biology of Infectious Diseases RU site, and also the Center for Ecology of Infectious Diseases, which some of you may be familiar with as, really one of the leading institutions of thinking about the ecology and just really infectious diseases in general. And that specifically is a research unit of roughly 65 faculty, postdoctoral associates, and student researchers that coordinates research activities across, really a wide range of disciplines and focuses on understanding the biology of infectious diseases at multiple scales. And Dr. Drake's research uses mathematics, statistics, and data science alongside experimental data to understand the dynamics of biological populations with a focus on ecological tipping points, the ecology of emerging infectious diseases, and extinction. And Dr. Drake's research projects are quite broad. And so I will just highlight one of his key focus areas so I don't take up all of his speaking time myself. And really, he is just one of the key leaders attempting to understand and predict dynamics of infectious diseases at the human-wildlife boundary, focusing on theoretical and also applied work to understanding and predicting spillover events of emerging infectious diseases. And he has developed theoretical models towards forecasting both seasonal and non-seasonal infectious diseases in terms of their emergence dynamics, with looking at and identifying early warning signals for those emergence events. He's looked at a yellow fever spillover risk in Brazil, and he's also identified the seasonality and other governing dynamics and predictive factors for Ebola spillover events in Africa. And then following the Zika epidemic, he's also worked on methods to anticipate other high-risk flaviviruses that might emerge in humans in the future to try and assist in surveillance efforts. And one of the things I most admire about Dr. Drake is really his dedication to teaching others. I mentioned that he was foundational for the REU program at the University of Georgia. And I was lucky enough to actually take a class taught by him alongside Pedro Hani at CISMID in the summer of 2014, which really was, it was the first class I took at CISMID, and it really was the start of my infectious disease modeling career. And as many of you probably know, I continually refer others to his material on his website from those CISMID workshops, which I think is one of the best resources for getting started with infectious disease modeling. Furthermore, he's recently been a regular science contributor at Forbes, which I think he's had quite a few really interesting articles, and I would really suggest everyone follow him on Forbes, as he posts about once a week, making just COVID-19 science accessible to the public. And I should just say to everyone, because I found him to be quite the good resource as well. In terms of COVID-19 research, he's carried out modeling work to understand suppression approaches to spread without needing intensive social distancing, and then also looked at trying to reconcile model predictions from sub-Saharan Africa with low reported cases. And with that, I will let him take it away.
Spencer, thank you very much for the introduction and the invitation to speak with you all this morning. Let's see. Do you see my screen? Great. as you did at UT, and I think in many other universities and organizations around the world, we started thinking about this coronavirus when we were seeing suspicious reports in the news out of China in the middle of January. Of course, Wuhan had their lockdown, I think that was on January 23rd, perhaps. The CDC had activated their Emergency Operations Center, I think 2 days prior, and we immediately launched within the Center for the Ecology of Infectious Diseases what we called the Coronavirus Working Group. At any given time, the working group typically is about 30 people, most of whom are students and just work a couple of hours a week, and has been, I think, as much an educational experience for them as it has been an opportunity for us to try and understand the epidemic in real time and to contribute what we can to the larger effort to mitigate spread and support our communities as they're facing down ongoing transmission. Much of our publicly available work is published on our website. We have not, for the most part, written this work up for academic publication, but have been working more in a real-time mode. But what we're calling the UGA coronavirus portal is available at covid19.uga.edu. There is a coronavirus tracker. It used to be called Yet Another Tracker, which we found particularly useful for visualizing the New York Times and Johns Hopkins data. There's preliminary reports of all of our modeling and academic work. There are regular forecasts based on our model, and the other kinds of things that you would expect to see there. The work of the working group, we have clustered into 4 different groups: for situation awareness, the development of dynamical models, a cluster that specifically focuses on intervention modeling. So this is the kind of thing that Spencer mentioned with Kara Brooks' paper, where we look at in the local or organizational context, doing sort of scenario analysis for different strategies that might be taken to mitigate spread, and then a number of projects that are focused on spatial modeling. One of the things that I'm most excited about at the moment is a model that we have for the county level spread, parameterized based on the sequence of counties reporting their first infection throughout the spring, and calibrated to the interventions that were taken in both the candidate, donor, and recipient counties. As a forecasting method, that's not very useful, wasn't helpful then, as spread occurred so rapidly. However, I'm anticipating that in later stages of transmission, it may be that that we see much more patchily distributed transmission at the end of the epidemic. And around that time, I would then expect states, counties, and municipalities to consider, once they've cleared the infection, how to keep it clear, and so possibly of use there. Another project in consultation with the CDC looked at estimating the importation risk throughout the spring and summer of cases from elsewhere in the world to U.S. ports of entry. So the kinds of things that that I suspect many of you are involved in and that you've seen from other universities, we also have our own flavor of all of those. So what I'll talk about today is a project where we've developed models for transmission of COVID in all 50 states, as well as the territories of the U.S. This is the scale that that we considered probably most actionable in terms of interventions, and it grew out of our initial work just focusing on the state of Georgia. And then we asked the question, well, can we take that work and automate it so that it can be updated regularly for the whole country? It turns out that problem was a greater challenge than we anticipated. So that's been quite an exciting bit of research that occurred throughout the summer. I'm going to spend a few minutes talking about our modeling, our process. If there's an opportunity to hear from some of you who've done some modeling, I'd like to compare notes about what you found tricky and what's worked. And then I'll show some of the results as well. One of the things that we've done is in the forecasting mode of our models, we've considered interventions primarily focused around policies that would restrict movement. So the shelter-in-place type policies that we saw in most parts of the country earlier in the year. And throughout, when you see red scenarios, those are return to pre-COVID levels of mobility and mixing. Green is status quo. If you do what you're doing right now, some states find that their red and green overlap significantly. And then blue is if you would implement a shelter-in-place order again. Some features of our model. It is a stochastic model. It's intrinsically stochastic with demographic stochasticity and incorporates realistic random variation. This is in contrast to a large number of models that we saw developed in April, May, and June, although I think throughout the summer, more stochastic models like this were developed by different groups. From the outset, largely prompted by our work on the 2014 to 2016 Ebola epidemic, we implemented what are in the jargon of modeling called the realistic waiting times or realistic interval distributions for the pre-symptomatic and symptomatic periods. In retrospect, I wonder if that was actually more complicated than necessary, but once we had developed our model in that direction, we stuck with it. The model was developed at a time when we had little understanding of the epidemiology and particularly the context of transmission. We did, however, anticipate pre-symptomatic transmission, and so our model was parameterized to allow for asymptomatic, pre-symptomatic, and symptomatic individuals all to transmit. And as we've accumulated more information throughout the summer, of course, we've updated our understanding of those processes. The initial model was developed in April when tests were, so the case definition was changing, tests were largely unavailable, and the distribution of tests particularly was influencing the case reporting rates. So we also considered time varying rates for case diagnosis and the probability of case detection. We believed then, and I still believe, that they were a significant part of the initial surge, so that the increased testing resulted in a reduction in, or an increase in the ascertainment rate, which was often confused both by the public and by modelers as substantial increase in cases. Of course, at the same time, case ascertainment was low, and so the actual number of cases was much higher than was being reported. Both are factors that we tried to account for in our model. When the data became available to us, we began using Unicast's platform for measuring mobility. So these are location-based cell phone records. We initially focused on their commuting data, which looks at the changes in the residency of cell phones for significant periods of time and those patterns as they are persistent through time. So basically, if there's a location where the cell phone is found to sit every night, that's considered home. If there's a location where the cell phone is found to sit every day, that's considered work. And so we measured the drop in the frequency of home to work movements. That's our measurement of mobility. We quickly became aware that this epidemic wasn't going to follow a pattern like, for instance, the foot and mouth disease in the UK, where you had an initial exponential growth of the epidemic followed by interventions that then result in containment. And so the wide range of interventions that have been taken to try and contain COVID result in unmeasurable processes that affect transmission. And so we developed our model to have a way of responding to that as well, which I'll refer to later as the latent process. And then finally, we tried to incorporate as best we could realistic intervention scenarios. And I feel fortunate that many of the decisions that we had to make early on, when relatively little was understood about transmission of SARS-CoV-2, I think we made reasonably good judgments, and so the model has served us well since then. So these are, so one of my concerns about many of the models that have been distributed is that they are not time varying. They don't account for the time varying nature of either the case reporting or the processes that are affecting transmission. And as a result, have to attribute all of the changes in case reports to transmission itself, which I think has led to sometimes erroneous conclusions. These are the ways in which we accounted for those, some of those time varying processes in our model. We considered that the transmissibility itself would be, through its effect on the encounter rate, would be reduced by a factor associated with this mobility. The top panel here shows what those reductions in mobility looked like in all 50 states. The blue line at the bottom is New York. And you can see that there was a pretty consistent pattern across the country, although with lag by some states vis-a-vis others, and largely a return to mobility that's somewhere around 80–85% of pre-COVID levels. The U shape you see here, of course, corresponds to the shelter-in-place directives throughout the late spring and early summer. We parametrically encoded the effect of decreasing time to diagnosis and the time to the increasing ascertainment rate, or the probability that an infection actually is detected. These plots show what that parametric function is. So the rough shape of the function, you can see that the time to diagnosis gets smaller and smaller over time. The detection probability gets larger and larger, but these are actually fit individually for each state that we model. This is what the model structure looks like. So this is a compartmental diagram. It has the usual S, E, I, and R components. We relabeled the E, or exposed compartment, to be latent, to signify that latently infected individuals may transmit just as much as those with active viremia. Those with active viremia are classified as being asymptomatic, symptomatic but undetected in the population, or symptomatic and detected. In this case, detected means not, in fact, yet in the case record, because there's a lag between the time at which an individual is infected, but it means that they'll eventually be detected. When they are detected, they proceed to the group of diagnosed cases. A diagnosed case may recover or be hospitalized. A hospitalized case may recover or die. And each of the L, I, C, and H compartments have 4 different dummy compartments within them, and that allows us to account for non-exponential distributions of time that people may persist in these different compartments. Importantly, C and H and D are the observed data streams to which we're fitting. Our model fitting routine allows us to use hospitalization counts when they're available to us, but doesn't require it. And so that also helps to facilitate modeling all of the 50 states. What I think is particularly important about our model is the way that we account for interventions, including generalized interventions like the wearing of face masks. This is through the force of infection. So basically, by modifying the transmission rate with a parameter that we refer to as omega, we can calibrate the transmission rate up and down. So omega is a factor that multiplies the basic transmission rate, and it consists of 4 factors that are themselves multiplicative. So these are the latent trend, the effect of mobility, any environmental noise, and then the constant estimated natural transmissibility. And we consider these to be multiplicative factors because we think of, in the usual way that we derive the force of infection, we think of encounters being through some kind of mass action interaction. These are based on encounter rates and then the probability of having an infectious encounter and the probability that that exposure results in transmission event. And so the latent trend is a factor that ranges from 0 to 1 that modulates how risky those encounters are. If you're wearing a face mask, presumably it's less risky than if you're not wearing a face mask. The effect of mobility we consider to be a factor ranging from 0 to 1 that modulates the encounter rate. And because all of these are modulated by a reduction, a multiplicative relationship between those is appropriate. The combined trend, omega, is made up of these two things, the mobility and the latent trend. Mobility is read directly off the data. So it's a covariate that's measured, updated routinely, and then the model is just fit with that coefficient. The latent trend is an underlying process for which we don't have covariates, but which is expected to fluctuate, to go up and down over time in response to, largely we are imagining this is capturing changes in behavior. And so it starts at 1 when everybody's behaving as they had before COVID, but then declines due to the wearing of face masks, individual protections like just maintaining social distance on a microscopic level, as when, for instance, people meet outside for exercise, let's say, but are not within the 6-foot radius or what have you. In any plots that we would have, mobility's in blue, the latent trend is in green, and then the product, which is really the factor that's modulating transmission, is in this pink or red color. For our latent trend, this is based on a fitted spline. We have regularized the spline by putting knots every 3 weeks. We've done some tuning of that. We don't have an empirical basis for making that decision, but roughly speaking, when we inspect what the outcome is, it seems to us to respond to what we understand around us anyway, as the patterns of changes in behavior as people adopt recommendations and so forth. And so this is a characteristic illustration of how these patterns changed over the course of about 4 or 5 months. We have derived the effective reproduction number for this model. I don't think that there's anything particularly intuitive about the formula itself, but the reason that this is helpful is because it allows us to evaluate the potential impact of interventions as well as the relative importance of different processes in deriving transmission analytically without having to run a huge number of simulations. Running simulations isn't particularly computationally costly, although because we're trying to apply it differently to all 50 states and the territories simultaneously, it does take a little bit of coding every time we want to set up a new scenario. But the estimation time is pretty significant. We're running on UGA's high performance cluster, and it takes us a little over 25 hours to do an update of our model. We previously were fitting the model and updating our website daily. We're now doing it roughly every 2 days because of that 25-hour turnaround time. Some details about model fitting. We use sequential Monte Carlo, particularly the POMP package that was written by Aaron King. POMP stands for Partially Observed Markov Process. What this means is that there is a connection between what's actually going on in the model, the state of the world, and one's observations of it, the data. But you're not assuming that those two things are equal to each other, that you've perfectly observed the world and you have an observation model that probabilistically relates the state of the system to the data that you have. In our case, the data are assumed to be negative binomially distributed. The data could be cases, they could be deaths, or they could be in some states, including Georgia, where we focused hospitalizations. Our estimation approach, of course, we've got a wide range of parameters. We've tried to inform the model and constrain it as much as possible based on information that we think is reliably obtained from case investigations. So parameters like the average incubation period or the average period of hospitalization are not fit. These are instead stipulated by us in advance based on you know, information in the literature, independent data that we have, that kind of thing, leaving a handful of free parameters, which are the ones that can be modified to try and fit the epidemic. These include the baseline transmission rate, the fraction of hospitalized cases resulting in death. Actually, that's not currently a step function. I'll come back to that near the end. Information about the variation in just random fluctuation due to what ecologists call environmental stochasticity. And basically that just refers to uncorrelated variation that happens over time for all kinds of random reasons. And then important parameters related to the observation process and the latent process. Our evaluation is probably not as rigorous as it should be. Right now, we're reporting mean absolute error over time for all of the states, and typically we get plots that look like this. What this illustrates is a common pattern that we've seen, which is that every time we do a model run, just about 45, 46 of the states work out beautifully. We have a model that we find compelling. It also fits the data well, and 4 or 5 states are not able to converge on plausible values. And which 4 or 5 states they are seems to change from time to time, which further makes automating the model fitting process difficult because we can't troubleshoot all of these models simultaneously every day. Let me give you some examples. Here is data from the state of Georgia. I actually need to check into what that the spike in the death notifications is. I imagine it's probably a reclassification. Importantly, our negative binomial observation process will handle that outlying data point just fine, and it doesn't significantly impact the fit of the model. So what you're seeing in blue here then is the data. In black is the fit model, and in gray is a forecast, I think, under the status quo scenario, where we assume that personal mobility stays the same as it has been for the recent past, and no additional shelter in place is ordered. Here's our example for Texas, and this would be, again, one of our well-fitting models. You can see our fits to the recent resurgence, and also our anticipation that that resurgence will continue under the status quo, and of course anticipating increasing number of fatal cases as well. Here's an example of a poor fit to data that would have a very large mean absolute error. In this case, probably what's going on is that there's an underlying dynamical change in one of our driving variables that's not adequately captured by our latent process. Sometimes this has been related to a discrepancy between the death notifications and the case reports. We had difficulty with some states throughout the summer as the mean age of infection was going down. That meant that the case fatality rate, where I'm referring to the fatality rate of case notifications, was therefore also going down. That caused the model to have a difficulty fitting both the death data and the case data at the same time. We've attempted to correct for that now by having a time-varying case fatality rate as well, which I suspect is responding both to the changes in the standard of care and treatments available for COVID patients, as well as the changing age distribution and consequent effects on the infection fatality rate. So we then put our model into sort of forecasting mode. We're forecasting 6 weeks out. I reckon that that's probably about 5 infection generations or so, which I think is really the furthest that one can reasonably expect to predict based on the role that behavior change has in driving this epidemic. When you have a time-varying process like this that is driven both by mobility and by mask wearing and all of the other generalized interventions that are being taken, I think there's a very interesting question about how you actually forecast. We do it in 2 steps. First, we've got 3 scenarios for mobility, which I described at the beginning. This is return to normal, status quo, and shelter in place. But then how do you model or forecast a latent trend, which is just, you know, a fit to what you've observed in the past? One of the things that we've found is that our latent trend is quite unstable in the most recent past. And this is just because of the nature of a cubic spline. So it's a sort of a statistical anomaly feature. I don't know. Just like ordinary extrapolation from the end of a linear regression is quite unreliable, so also here. And so what we do is we consider the mean of the latent trend over the 20 days preceding the last 10 days. So the mean of the latent trend from 30 days ago to 10 days ago. And consider a linear interpolation from the current state of the latent trend up to that mean as being the effect of these generalized unobservable interventions, mask wearing and so forth, going into the future. But I think it's an important thing to understand as part of what our forecasting process assumes. I've already mentioned the mobility scenarios, so return to normal, maintaining social distancing, or increase social distancing to 30% of normal. And then we get results like this. So using the White House definition of a red zone or a hot state, at the moment we're finding that 33 states are forecasted to be in the red zone for new cases at some point before December 22nd in both the status quo and the return to normal scenarios. But also in every case, increasing social distancing to that 30% level would bring the state out of the red zone by the same date. It's important to recognize that that increased social distancing is not related to that particular state's experience or history in the spring, but says they do what New York did in the spring, is what the scenario is envisioned there. You know, in order to make our model useful to people, we've created a dashboard, which is interactive. It's on our website, and you can use that to interactively investigate what the outputs are. There's no way for us to automate the validation of this. So every now and then we get an email from somebody saying, your model's doing something really wacky with my state today, and we go in and look at it. But for the most part, we've actually found it to be quite reliable in this semi-automated process. A couple of outlooks. Here's what it looks like where I am in the state of Georgia. My hope is that we will not see the resurgence that is being seen by much of the country right now. I think that's an open question. I was speaking to a doctor from some rural hospitals in Georgia, and his observations are that we are seeing increased case reports, but I think that those are so patchily distributed that we don't observe that at the state level. So here we're looking at case counts and daily case counts and deaths. Here we're looking at the total number of infected persons, both of which are reported on the website. We have the same data for Texas. I imagine that you've done similar scenario analyses yourselves. here's one of those cases where there's a significant amount of overlap between the return to normal and the status quo, which probably reflects the fact that mobility patterns in Texas have largely returned to their pre-COVID levels. The difference then being driven primarily by this latent process capturing things like mask wearing and microsocial distancing. We predict that daily new infections per 100K could easily get into the hundreds per day. What are you actually reporting right now? If Spencer or somebody's unmuted, I'm just curious. I didn't check before signing on this morning.
Our estimate of like currently infectious people?
Yeah, per day.
Michael, do you happen to know? I think you just posted it, but I can probably pull it up in a second.
So new infections per day. What are your case notifications per day like right now?
We're looking at hospitalizations. It's like I can go into the model, but it's not so easy.
Well,
the
that's
cases
fine.
are running between 10 and 11,000 per day.
Okay.
Yeah, so we the main estimate we're giving is probably not necessarily the new infection, so it might be hard to extrapolate, but we're estimating across the state a prevalence of about 8 per 1,000. And so currently infectious people right now, 8 per 1,000. So I don't know, I guess you could probably divide that by 7 to get new infections each day. So about 1.5 per 1,000.
Okay. So that would be 800 per 100,000, which divided by 7 gives you a little bit more than 100 new infections per day, which, here our status quo scenario is giving, somewhere between, it looks like about 80 and 210, 215. So pretty consistent with what you're observing. A couple of other scenarios. Here we look at Oklahoma, daily cases and deaths scenario, not that different to Texas. Here's an example for Arkansas. Interestingly, normal mobility doesn't appear to have as dramatic effect as it does in Georgia, Oklahoma, and Texas. And here are some of the death rate predictions. So we're seeing cumulative cases and deaths roughly, increasing slowly in Georgia, with the potential to increase dramatically in places like Texas. I thought I had Oklahoma and Arkansas again, but I don't. So again, just the same kind of scenario analysis that I think is being done widely by modelers, and I found it useful to compare with other people and finding out what they've done as well. So just a couple of high points, key findings and takeaways. Our model projects that increasing social distancing really could have an effect again. I think that we've accounted for the ways in which the population is compensated through mask wearing, sneeze guards, and other interventions through our latent process. And I'm doubtful that there's much scope for improving intervention effectiveness there at this point. We've learned a lot about fitting complex models. We've also met occasionally with Aaron Mordecai's group at Stanford to compare notes. We're discovering that they're having the same kinds of issues in terms of model fitting and the difficulty of fitting a panel of models simultaneously. I don't know if you're doing that, but if you are, I'd be interested to hear more about that. We've developed some new techniques to help us with that. A context-aware parameter initialization, what we call the warm start, which helps to speed up our estimation process. Our focus on sort of hybrid calibration that uses both direct case investigation information as well as fitting to population level data. I think there's a long way for us to go methodologically. One of the things I had hoped to do was to get us to a full sort of Bayesian approach where we could incorporate prior information in a probabilistic way. We've found that to be unachievable at the current time. We have recently modified our model so that the case fatality rate is a smoothly time varying function to account for the changing age distribution as well as effectiveness of treatment. We think that this is significantly improving our model fits. And by and large, now what we're doing is trying to keep the ship running and fine tuning it as we go along. That concludes my talk. If you're really interested, we are eager for feedback and assistance. Our code's available on an open website that's shown here. There have been a large number of people contributing to this model, but the main developers besides myself have been Andreas Handel and Andrew Tredenik, and I want to be sure to give them credit for this. And thank you all very much for your time this morning, and Spencer for the invitation to speak.